Hi, everyone. A big welcome to today's training course. Today we are going to talk about carbon flow diagram and balance equation of some of the non-carbon models. I'm Yuan Huang. I'm a research scientist in Ceylon, Australia. In today's lecture, I'm going to introduce you some basic concepts we frequently use in deriving non-carbon models. They may sound simple, but when you piece them together, you may end up understanding very complex system models. The goal of today's lecture and practice are to understand carbon flow diagram and balance equations, to be able to derive very generic carbon balance equations from carbon flow diagram and vice versa. I bet you have already run into a variety of flow diagrams in different forms, complexity, and for different purposes. For example, we could draw a very simple flow diagram like this one to help us diagnose what might be the issue and what to do when a lamp stops working. Or you may have already read more complex flow diagram like this global food system or the classic carbon flow diagram from the IPCC report. In non-carbon models, we are generally interested in tracking matter and energy in different space and time across our global net, and answering questions related to when, how, where, and how much of those transfers occur. A flow diagram is therefore very helpful in conceptualizing our issues, classifying our starting boundaries, and disentangling very complex interactions, etc. Depending on our scientific questions, in addition to carbon, sometimes we also track, for example, water, nutrients, and energy in carbon models, as they are a critical environment that drive and interact with the carbon cycle. In our training course, we focus mainly on carbon dynamics, but a lot of rules and methods introduced here are also applicable to water, nutrients, and energy, etc. We use the term stock, or sometimes we call it storage, flow, or flux very frequently in track carbon dynamics. Suppose that you have a bank account. The total amount of money in your bank account is the stock. Every month you put a certain amount of money into your account, for example, from your salary, or you also take some money out of your account each month. For example, your everyday expenses. This deposit and withdraw is the flow on into and out of the account. The same concept applies to carbon. We could take total carbon in the atmosphere, for example, as our stock, and we track carbon flows into and out of the atmosphere to know the dynamics of carbon stock in the atmosphere. The law that enables us to track carbon dynamics is the conservation of mass. Without nuclear reactions, matter can neither be created nor destroyed, but the chemical structure and physical form can change. Most carbon in the atmosphere is in the form of carbon dioxide. It could be assimilated by plants to form carbohydrates or sugar, or sometimes we call it organic carbon, through photosynthesis. The amount of carbon moves out of the atmosphere is the same as the amount of carbon enters plants. As organic carbon, if we quantify the carbon in weight of carbon atom. For the system we study, we need to know all the boundaries of our system, to know what are our stocks and what are those fluxes, and also in which direction are those fluxes moving. Take the terrestrial process of carbon flow as an example. If we take the terrestrial plant as our starting system, carbon in plants is our carbon stock. Carbon flows through photosynthesis that turns carbon dioxide into organic carbon is our incoming flow. carbon flux through plant respiration that involves using the sugar produced during photosynthesis plus some oxygen to produce energy for plant growth. It's one of our outgoing carbon flow. Drops of leaf, fine roots, branches, etc. under unfavorable conditions, that is the lithophore, is our second outgoing flow for this system. If we take soil carbon, soil as our starting system, soil carbon is our stock. Lithophore now turns into an incoming flux for our starting system. Soil respiration is the outgoing carbon flux, and soil lost during runoff is a second outgoing flux. If we take plants and soil together as our system, the the carbon stock is the total carbon in plants and soil. The incoming carbon flux is the carbon through photosynthesis, and the outgoing fluxes are plant respiration, soil respiration, and also the carbon lost through runoff. Now, lithophore is no longer the incoming or outgoing flows. It's the internal flow between plants and soil. If we are only interested in the total carbon in plants and soil, we are no longer track lithophore anymore. So after we are clear on what are our carbon stock and what are our flux, if we know the numbers of those fluxes and the carbon stock at the beginning, or the initial carbon pool size in our modeling term, we could track the dynamics of a carbon pool through time. The idea is that the change in the carbon pool size is always equal to the total incoming minus the outgoing carbon flows. Suppose we have a carbon pool, I call it X here, that has a weight of 30,000 grams of carbon. Or think about you have $30,000 in your bank account at the beginning, that is when t equals 0. We have an incoming flux that is 2,000 grams of carbon per year. Sorry, it is too small if it is your annual salary. I call the input rate here I. And suppose that your income is relatively stable and do not change with time. For the outgoing flow, if we have a bigger plant, normally we end up with more respiration. That is, we spend more when we have more money in our bank account. Suppose 20% of carbon in a plant pool is used up through respiration every year. That is a turnover rate K equals 0.2 per year. So the question we would like to ask is how much carbon will we have at the end of the year or at the beginning of next year? So here our time step is 1 year. When t equals 0, we have a carbon pool that is 30,000 grams of carbon. And we have an input rate I, that is 2,000 grams carbon per year, and turnover rate 0.2 per year. So when t equals 1, the pool size at t equals 1 equals the pool size at t equals 0 plus the total income flow and minus the total outgoing flow. That is 30,000 plus the total income flow is the input rate multiplied by the time. That is 2,000 multiplied 1. And the outgoing flow is pool size dependent, which is the turnover rate 0.2 per year multiply the pool size, that is 30,000 multiply the time step, that is 1 year, which gives us 26,000 grams of carbon. So if you are curious, you want to know what is the size of our carbon pool 1 year forward in time, that is when t equals 2. It's the same logic when T equals 2, the carbon pore size equals the carbon pore size of the previous time step, that is X at T equals 1, plus the total income carbon flux minus the outgoing carbon flux. So the pore size at T equals 1 is now 26,000 grams per carbon. So the input rate is the same, the time step is the same, that is 2000 multiply 1, while the outgoing flow, we have the same turnover rate, that is 0.2, but the pore size is different. The pore size now is 26,000. The time step is the same, 1 year. So this gives us 22,800. So with the same logic, you can derive the carbon stock in the third, fourth, fifth, etc. years. The mathematical equation says that the carbon pore size at the next time step is always equal the carbon pore size at the previous time step plus the total income flow minus the total outgoing flow, that is the conservation of mass. This is also an old method. As a numerical method, we sometimes apply to solve the differential equation I'm going to introduce in the next slide. So now we know how to derive x at the next time step from this equation. If we would like to know the change of x, so we move x at t from the right hand of the equation to the left hand of the equation, which gives us the delta t equals the total income flux minus the total outgoing flux. If we want to know the rate of change of the carbon pool, we divide both the left hand and the right hand of the equation by delta t, which gives us this difference form of the carbon balance equation, which says the rate of change equals the input rate minus the outgoing rate. Note, in the example from the previous slides, we assume the time step here, delta t, is 1 year. So when delta t is infinitely small, that is when it approaches 0, the difference equation could be written as the following differential equation. Both the difference and differential equation are our carbon balance equations, which says that the change of the carbon pool equals the income minus the outgoing. So if we have two carbon pools in our system, and suppose the outgoing carbon flux of one pool becomes the incoming carbon flux into the other carbon pool. So think about the plant soil system introduced earlier. Well, the neutral flow is the outgoing flow of the plant pool and also the incoming flow into the soil carbon pool. The carbon balance equation in a differential form writes the same as the one pool case as we showed earlier. The carbon balance equation for the second carbon pool also takes the form that the change in the carbon pool size always equals the inputs minus the outputs. So suppose for the input into the second carbon pool, it is a fraction of the total outgoing flux from the first carbon pool. I call the fraction F1. And the total outgoing carbon flow here is K1 multiply X1. So here goes our carbon balance equation for the second carbon pool. The logic applies to multiple pool models. For each pool, we need to know what is the incoming and what is the outgoing flux. Here I show the carbon flow diagram for two carbon models. The left one is the classic soil carbon model, the century model, The right one is the TICO model. Both models conceptualize our natural carbon cycling into different compartments, that is, different carbon pools with different characteristics, and tracks the transfers among different carbon pools, indicated by those arrows. The transfers could be parameterized as a single constant, or we could also model those transfers with different functional forms to capture the complex interactions with, for example, climate and soil conditions. We take the TICO model here as an example to illustrate how to derive a system of carbon balance equations from the carbon flow diagram. In this carbon flow diagram, we have 7 carbon pools, 2 plant carbon pools, the foliage biomass and woody biomass, 2 litter carbon pool, the metabolic litter and the structure litter, 3 soil organic carbon pool, the soil microbes, the small soil organic matter, and passive soil organic matter. For each of these carbon pool, we need to find what are the fluxes comes into and goes out of these carbon pools, represented by the arrows. To make it easier to write mathematical equations, I used the symbol x1 to x7 to represent these carbon pools. Carbon flux through photosynthesis is the external carbon input into our system of 7 pools. I call the total input rate here I. A fraction of those total inputs is allocated into foliage biomass. I call this fraction beta 1. And a second fraction is allocated into the woody biomass. I call the fraction beta 2. So for the carbon balance equation of the foliage carbon pool, it goes as this one. It basically says the change of the pool size equals the input rate minus the outgoing. The input rate is the total input I multiplied by the fraction that is allocated into this carbon pool, beta 1. For the outgoing flux, as we talked earlier, it's a pool size dependent. It's the turnover rate, K1, multiplied by the pool size x1. Similarly, for the woody biomass pool, x2, the change of the pool size equals the input I multiplied by the allocation fraction, beta 2, minus the outgoing flux, K2, x2. As you can see, to write the carbon balance equation for each of the carbon pool, we basically need to find what are those income and what are those outgoing, and how to formalize those input and outgoing flux. In some cases, there may not be only one income streams. For example, here in this carbon pool, the structure litter carbon pool X4. As you can see, there are 2 arrows goes into this carbon pool. One is from X1 and one is from X2. So for the carbon balance equation of X4, there are 2 items of the input flux. For the input from X1 to X4, the total outgoing from X1 is Q1 multiplied X1. A fraction of the total outgoing is transferred into the structure litter X4. I call this fraction I41. So the income flux from X1 and X4 goes as I41 multiplied K1 and X1. Similarly, for the transfer from X2 to X4, it goes as F42 multiplied K2 X2. As you can see, for the total outgoing from X1, a fraction is transferred to X4, and a fraction goes to X3, and a fraction goes as carbon dioxide into the atmosphere. So in theory, F41 should be smaller than 1. So let's have a look at the outgoing flux. So for the sake of X4, we don't really need to know how much of the carbon goes into microbes, how much goes into carbon dioxide, how much into snow, soil organic matter, but we need to know the total carbon flux goes into the fourth carbon pool. Similarly, assume that the outgoing flux is pore size dependent, is K4 multiplied by X4. So as you can see, the same procedure can be applied to different carbon pools. We need to account how many arrows goes into a corresponding carbon pool and how many goes out. One arrow normally corresponds to one flux term. Since the boundary of our system is the 7 soil organic carbon, that is, I only interested in the total amount in each of these organic carbon pool. I'm not interested in the carbon dioxide that goes out of the system, so we don't really track the carbon dioxide here. Here is a second multiple carbon pool example. The liter and soil organic carbon components of the OKD model. In this version, I do not separate the organic carbon according to the soil depth. So we track 7 organic carbon pools. That is 4 liter carbon pools and 3 soil organic carbon pools. So we have here 7 carbon balance equations. The idea is the same as what we have done for the TICO model. We track those arrows comes into and goes out of each of the carbon pool. For example, here an active soil organic carbon pool X5, we have 1, 2, 3, 4, 5, 6 arrows goes into this carbon pool. So for the carbon balance equation, we have 5 incoming fluxes. I use the symbol F51 to represent the fraction of outgoing flux from X1 goes into X5. In a real model, sometimes we may only need a simple parameter to parameterize this fraction. Sometimes we may need a very complex function or functions to capture the complex interactions with different factors in the real world. So when we have a very small number of carbon pools, it's not that difficult for us to write down the carbon balance equation one by one. So if we have many carbon pools, for example, 100 here for this version of the OKD model that tracks soil organic carbon dynamics at different soil depths. How about the carbon balance equation? Let me give a little bit introduction on this model. So similarly as the previous example, here we track 7 different types of organic carbon, that is 4 liter types and 3 soil organic carbon. What is different from the previous example is that in this OKD mixed model, we have 32 soil layers. For each of the soil layer, we have active, snow, and passive soil organic carbon pools. Well, the reason to have vertical soil layers is to try to mimic the nature more realistically, especially in those permafrost region. So in total, we have 72 multiplied by 3 plus 4, that is 100 carbon pools. Instead of writing down the carbon balance equation one by one, I put them together into this matrix equation. So it says basically the same thing. The rate of change of the carbon pool equals the input minus the output. Now, it's not that obvious to spot out what are our input and which is the output. It depends on the sign of the matrix element. The first item on the right-hand side of this equation summarizes the external input into the system. The second block of this matrix summarizes the turnover rate and transfers of fluxes among different organic carbon types. And the third block of matrix indicates the vertical processes between adjacent soil layers, which may be linked to processes such as bioturbation, diffusion, and advection. Depending on the structure of the model, the matrix equation could also take slightly different form. For example, on the left-hand side, I show the flow diagram of part of the CLM 4.5 model. CLM 4.5 tracks coarse-woody debris, metabolic litter, cellulose litter, and the lignin litter, and also fast snow and passive organic carbon in 10 soil layers. Different from OKD mix, CLM also tracks the vertical distribution of litter. The matrix equation here takes a similar form, but items in each matrix are different. The dimension of the CLM 4.5 matrices are 70 by 70, corresponding to 70 organic matter pools, while the OKD mix, the dimension is 100 by 100. I will talk in more details about the matrix version of this carbon balance equation tomorrow, so don't worry if you don't understand here. So if you understand the basic concept I introduced here, and a big congratulations, because those very complex Earth system models are built upon this basic unit step by step. Here I take the CLM model, the community land model as an example. What we have talked introduced earlier is only the background carbon part of this model. This model also tracks the background vegetation dynamics, the nitrogen cycle, the hydrology, the surface energy, as well as interactions among these components across different land cover types. If we look into a big picture, land is only one component of this big Earth system model, which also tracks dynamics in atmosphere, the ocean, and on the ice to allow us to look into Earth's past, present, and future climate. It's important to understand the basics before we get overwhelmed by the complexity. Thank you all for today, and I hope you enjoyed today's lecture.